Let's turn our attention now to brushless DC motors. And you'll see that the topology is actually quite different from a brushed DC motor in the sense that the coils are now actually on the stator and the permanent magnet is on the rotor. So it's like we took our brushed DC motor and flipped it inside out to create this topology. And what I'm going to do is I'm going to pass some current through this coil in such a way that it creates a north pole in the air gap on the top stator piece, and it'll create a south pole in the air gap on the bottom stator piece. Now I'm going to put a hand crank on this motor, and I'm going to essentially rotate it through 360 degrees, as you can see here. And what I'm doing is I'm plotting the torque that the motor is generating as it's rotating. Now I will tell you that I've never seen a motor that had this beautiful of a torque waveform, and it's almost impossible to achieve because you would have to have uniform flux density in the air gap in order to get that kind of performance, and no motor can achieve that. But for the moment, let's just assume that that's what I've got and that that's what the waveform looks like. So right there at angle equals 0, we see that that's not a point that the motor wants to be in because I've got a north pole fighting against a north pole and a south pole fighting against the south pole. But nonetheless, all the force that's being produced on that rotor is right through the center of it, so therefore the net torque is 0. And if I knock it off of that center position by just a little bit, it's going to swing around to this position right here, and that's where the motor actually wants to be, where I have attraction between the rotor and stator magnets. And if I try to offset that rotor from that position, either from a clockwise point of view or a counterclockwise point of view, notice the torque that the motor produces. It actually fights me to get back to that state where it wants to be at, which is, sometimes I refer to that as the happy state of the motor. So the motor's just sitting there, it's all happy and everything, but it's not producing any torque for me. How do I get the motor to actually rotate another 180 degrees? Well, the answer is I need to change the polarity of the currents in my stator coils. So if I do that, what that essentially does is that will now invert the torque curve from its original position. But the problem is, in order to get back to that other angle, 0 degrees, I don't know whether it's going to go in a clockwise direction or a counterclockwise direction. It's actually undefined. A perturbation in either direction could send the motor flying off in that particular direction. So this non-deterministic performance of this single-phase brushless DC motor is not acceptable, and we need to find a way to get around that, and that's done in the next slide. So to get around this undeterministic nature in terms of which direction the motor will want to spin, the solution is we add more phases to the stator. So in this case right here, I'm going to turn on some current to phase A, and when I put a rotor inside that stator structure, it's going to line up in the direction as shown here. Now what do you suppose I would have to do in order to get the motor to spin in a clockwise direction? Well, the answer is I would want to take the current out of phase A and put it into phase C. In particular, in this case, it would be negative current into phase C, and that will cause the rotor to now try to line up with the phase C stator poles. Now this process of taking the current out of one coil and putting it in another coil, it has a specific name in motor control. It's called commutation. And basically, commutation means taking the current out of one circuit and putting it into another circuit. So in this case, I've taken the current out of coil A, I've put it in coil C, and the rotor now wants to align with the stator poles of coil C. And I can continue this commutation process and make the motor continue to spin around following the rotating magnetic field of the stator as shown in this diagram. However, this is not a very efficient way to control a brushless DC motor. In fact, if you look, I'm only controlling one stator phase at any given time, and that means that 2 out of the 3 coils are not being used for anything. There's actually a better way to do it, and let's take a look at that in the next slide. So here I have my 3-phase stator arrangement with the rotor inside of it. And what I'd like to do is to come up with a procedure by which I can drive multiple coils to generate positive or negative torque. So the way I'm going to do this is I'm going to put positive current into all 3 phases of the motor at the same time. And then once again I'm going to put like a hand crank on the motor, and I'm going to spin it, I'm going to rotate it very gently through 360 degrees. Now the torque waveform that you see for phase A, that's the same one that we saw in the first slide when we talked about brushless DC motors. But what you'll notice is that the torque waveforms for phase B and phase C are identical to this. The only difference is they're separated in phase by 120 degrees, and that's because the B and C coils are separated from phase A spatially by 120 degrees. So we end up with torque waveforms that look like this. Now, by looking at each one of those commutation intervals, here's the rule that I'm going to apply. If positive current in a particular coil for that commutation interval will result in positive torque, I'm going to leave it alone. I'm not going to do anything to it. But if positive current in a particular commutation interval results in negative torque, then if I want positive torque, then what I have to do is I have to flip the current over. I have to invert the current for that particular commutation interval for that phase. And then the only one that's left is, what do I do with those commutation intervals where the torque is actually transitioning from low to high or high to low? Well, in this case, I think I'm just going to turn that coil off during that period of time and not do anything with it. So that's the rule. And if I apply that rule consistently to all phases, all three phases, in all the commutation zones, I end up getting a current waveform that looks like this. So now, when I actually rotate the motor through 360 degrees, look what happens to the torque waveform. And as you can see, in every case I have commutation intervals where two phases are contributing to positive torque and one phase is contributing zero torque. That means, assuming that I have torque waveforms that look exactly like the ones shown here, if I add up the total torque in each one of the commutation intervals, it's actually the contribution of two torques from two phases, which are perfectly flat. That means that my torque in my machine for every interval at every instant is always going to be a constant torque. Now there's something else that we can notice by looking at the current waveforms that's rather interesting. In every commutation interval, I will have one phase that has positive current and another phase that has negative current, and then a third phase which is turned off. So maybe I can reuse that current in multiple phases. For example, let's look at this commutation zone right here, the first one. In this case, I've got positive A current and negative B current. So what I'm going to do is to take all of the bar phases, in other words, all of the stator poles that have the winding wound in the opposite direction to create an opposite magnetic polarity in the air gap. And I'm going to take all those bar phases, tie them together inside the motor. And that point is going to be called the neutral point. So now I've basically connected all the phases together, and I can actually have current shared between different phases. So let's take an example where I'm going to take phase A and I'm going to pull it high with a transistor so that it's pulled up to the positive DC bus voltage. And I've got another transistor tied to phase B and it's pulled down to ground. Let's follow the current path. So in this case right here, current is going to flow through phase A, go through that coil, jump down to the phase A bar pole piece, and then it's going to hit the neutral node. It's going to go over here to phase B bar, go around that stator pole piece, and then finally out through phase B and then to ground. So you can see that with this kind of a diagram, we can actually recreate the scenario in the waveforms to the right-hand side of the graph, where the positive current in one phase can actually become the negative current in another phase. So I can take the procedure that I defined in the previous slide and implement that in some kind of controller, whether it be some logic gates or a microcontroller, microprocessor. There's lots of different ways to do that. But there's just one catch to this whole process, and that is, in order for me to know which transistors I should turn on or turn off, I need to know where the rotor position is. So that's why I have this Hall effect arrangement on the back end of my motor. Here's a little magnetic disc. In this case, it's got 4 pole pieces on it, and I've got 3 Hall effect sensors separated from each other by 120 degrees. Now these are digital Hall effect sensors, which means they don't really detect the absolute analog field strength of the little magnetic disc. All it's detecting is when I transition from a north pole to a south pole and vice versa. So I have 3 wires, each of them carrying binary information. That's 2 to the 3rd power. That's 8 possible conditions that can be detected from my Hall effect arrangement here. But it turns out that with 120 degree spacing on my Hall effect sensors like this, I will never get the condition of 0, 0, 0 or 1, 1, 1. So if my controller ever sees those two codes coming back, that means that there's a fault. Either my connector has pulled loose from my Hall effect sensors, or my power supply has gone dead for the Hall effect sensors, or something bad has happened, and it can flag that as a fault. But the remaining states, the 6 remaining states, are all actually legitimate states. So I can take that information, use that on the input of my controller, and my controller then knows where the rotor is, and from that information it knows exactly what commutation zone that it needs to apply to either generate positive or negative torque.